Hello all. Now we will start learning the various transducers and sensors used in mechatronics. We will begin with the measurement and control of temperature. Temperature sensors they uses the expansion of solids, liquids, or gases, or the change in the thermal resistance, or even the development of thermoelectric EMFs. Now the first one is the bimetallic strip. Bimetallic strip actually it utilizes the concept of the coefficient of thermal expansion. Most of the metals and alloys they have a coefficient of thermal expansion. They expand with an increase in the temperature, which the rate of the expansion is governed by this coefficient of thermal expansion. A bimetallic strip essentially consists of two different metals which are shown in different color in this diagram. They have different coefficient of thermal expansions. Now, in the initial state, in the room temperature, both these strips they are of equal length, and two strips are bonded together at the two ends. Okay, so that they can't expand freely. Now, initially in the room temperature, this strip is straight and the connections or the circuit is complete with the contact here. Now, as the circuit gets completed, the current flows and the domestic equipment starts heating up. With an increase in the temperature, the strip also starts to get heated up and it expands. Now, as the strip consists of the two different metals, the expansion of the two different metals are not uniform or not the same. They expand at different rate. But since the strips are bonded together at the two ends, they can't expand as they wish, which means that the strip having the high expansivity, high coefficient of thermal expansion, it expands more, and the strip having the low expansivity, it tries to control the expansion of the other material, the other strip. As a result, a curved shape is formed with the material having high coefficient of thermal expansion on the outside and the second material on the inside. Now, due to this curved shape, the contact between the strip and the temperature adjustment is lost and the circuit is now open. Hence, the current will not be flowing and the system starts to cool down. As the temperature starts decreasing, the strip also tries to go back to its original position, and once a lower temperature is reached, the strip is again to this original position and the contact is made and the cycle repeats. So this mechanism is utilized as a temperature control switch in domestic equipments such as a thermostat or the iron box. Now the a knob is used for the temperature adjustment. Now by turning the knob, the position of between the strip and this point can be altered. The higher the temperature to be reached, the knob can be turned clockwise. The thermostat also utilizes a small magnet. This enables the hysteresis property, which means that the strip after reaching the set temperature regains its original form at a lower temperature rather than the initial one. So this is how a bimetallic strip is used for the temperature control in a thermostat or other domestic appliances. The next one is the resistance temperature detectors. Now for most of the metal, the resistance increases in a linear way with increase in temperature. As seen from the graph, with an increase in the temperature, the relative resistance tends to increase almost linearly. This behavior is different from different materials such as nickel, copper, platinum, the nickel copper alloys, etc. Now this behavior is governed by an equation given by RT equal to R0 into 1 plus alpha T, where alpha is the coefficient of resistance and it is different for different materials. The RT is the resistance at a temperature T degrees Celsius and R0 is the resistance of the material at 0 degrees Celsius. T is the temperature at in degrees Celsius. Now this variation of the resistance can be calibrated to measure the temperature of the material. This is how the RTDs work. Now RTDs are simple resistive elements in the forms of coils of wires of metals such as nickel, copper, platinum or alloys of nickel, copper, etc. Now the platinum is the most widely used for these RTDs as it has a purely linear relationship compared to the other metals. Uh, Now these RTDs are highly stable. They can reproduce the responses for a long period of time and over a large temperature range. And they can also have response times of zero point 0.5 to 5 seconds. Now the RTDs are made of in the form of thin films as well as the wire wound elements. Now in the case of a thin film, the metal is deposited on a substrate which is mostly ceramic substrate. In the case of a wire wound element, the platinum wire is wound on a high temperature glass adhesive which is covered in a ceramic tube. The third one is the thermistors. These are the semiconductors made from the mixtures of oxides of metals such as chromium, cobalt, iron, manganese and nickel. They are available in various shapes such as disc, rod and beads. Just like the metals, the thermistors also change their resistances with respect to temperature. However, unlike the case of metals, here the resistance decreases in a very non-linear manner with an increase in the temperature. This is shown in the graph where the resistances decrease exponentially with an increase in the temperature values. Now the graph is governed by the equation RT equal to K into e raised to beta by T, where K and beta are the constants which is varies for different materials. RT is the resistance value at a temperature T degrees Celsius. Now since the resistances decreases with an increase in temperature, these thermistors have a negative temperature coefficients. Now they are very rugged and can be very small. Thus, we can use a thermistor to measure the monitor the temperature at a literally at a point, and this gives the rapid responses. They are used with my electronic systems for cars to monitor the air temperatures as well as the coolant air temperatures. So the next temperature sensor is the thermodiodes. These are junction semiconductor diodes which are widely used as temperature sensors. Now, when in the case of doped semiconductors, which means that there is an induced impurities at the junctions, when the temperature of these doped semiconductors changes, the mobility of the charge carrier will be changing, which means that the rate at which the electrons and holes can diffuse across the p-n junction will be affected. So whenever there is a potential difference across the p-n junction, the current through the junction will be a function of the temperature, which is given by I equal to I0 into e raised to EV by kt minus 1. Here I is the current and V is the voltage or potential difference. Now T is the temperature. Now K and I0 are constants for a given material, where I0 is the current at 0 degrees Celsius. Now taking the logs, the equation will be changed into in terms of voltage, like V equal to kt by E into log I by I0 plus 1. Now if we observe the equation, we can see that K for a material K and I0 is constant. So for a given material at a constant current I, the voltage will be proportional to the temperature on Kelvin scale. This means that if we measure the potential difference across a diode at a constant current, it can be used as a indicator to measure the temperature. This is how the thermodiodes are used to measure the temperature. Now similar to the thermistors which we studied earlier, Thermodiodes are also compact. However, unlike the thermistor, which gives a nonlinear inverse response to a temperature change, here the thermodiodes gives a linear response to a change in temperature, which is very much helpful for the measurement. Now, with necessary signal conditioning, these thermodiodes can be formed as integrated circuits to form very small sensors, for example, LM3911. Such thermodiodes can be used to measure temperatures at a single point.